Well, as we continue our topic on gases, I want to talk about this idea of an ideal gas. And we've got three things that have to be true in order for a gas to be considered to be ideal. These are listed for you on page 300, but I've got them typed out here. An ideal gas is one in which the molecules or atoms occupy no volume. Now, when we learned about what matter was at the very beginning of this course, we said matter was anything that has mass and takes up space. So if matter has to take up space, it's not possible for this gas to occupy no volume. All right, so this is a theoretical concept. It's not actually possible, but we're going to define these terms and then we're going to explain what the scenario has to be in order for a gas to behave close to ideally so that we can use the associated equations with ideal gases. So anyway, must occupy no volume. That's number one. Number two, the molecules or atoms can't be attracted to one another. So there's no, that they're trying to come together. In other words, they're floating around freely. There's nothing that's causing them to clump up or anything like that. And sort of along the same lines, I just realized I didn't capitalize the C. That's going to bug me. Let's fix that. There we go. Sort of along the same lines, they don't clump up. When a collision happens between the molecules, they're just going to bounce off. They're just going to repel one another, and there won't be any energy lost whenever they bump into one another if it's an ideal gas. That's also true that whatever container it's in, we assume that the collisions are elastic. In other words, there's no energy lost as it hits the container walls or as these molecules or atoms bump into one another. So technically, no gas behaves this way, but under certain conditions, a gas will behave close to ideally, and that condition is if a gas. Let me just put a little asterisk here. That was a terrible asterisk. Let's try that again. That's a little better. A gas behaves ideally if the following is true. If it has a high T, high temperature, all right, which for our case, it has to be greater than, T has to be greater than 0 degrees Celsius, and if it has a low pressure, all right, and by low pressure, we're going to say a pressure that is less than or equal to 1 atm, all right. So a temperature that's greater than or equal to 0 degrees Celsius, or a pressure that is less than or equal to 1 atm. In that case, we would say that this gas behaves ideally, all right? And so these values here, 1 atm and 0 degrees Celsius, are important values because that's what we call STP, standard temperature and pressure, all right? So if you see a problem that just says you're at STP, it means the temperature is 0 degrees Celsius and the pressure is 1 atm, and we can assume a gas that's in that state behaves ideally, all right? So if the temp is near or above 0 degrees Celsius or the pressure is near or below 1 atm, then we can assume it behaves ideally, and that means, the benefit of that, it means that we can use what we call the ideal gas law equation. So let's define that. Whoops, that is not what that was supposed to do. I guess I'm just going to delete the whole thing. So the ideal gas law equation, what is that? Ideal gas law. All right, so if the gas behaves ideally, we can use this equation, and the ideal gas law equation is PV equals nRT. Now, you already know P is pressure, V is volume, T is temperature. We've used that in our other equations. What's new is this N here. And N is the number of moles of the gas that we have, all right? And then R is a totally new concept. It's a constant. It's the ideal gas law constant, all right? And we've had constants in equations before where it was a constant, but it was only a constant for a particular molecule or for a particular atom. In this case, though, the ideal gas law constant is always the same thing, regardless of which type of gas you're dealing with. And the ideal gas law constant is 0.0821. It's got some strange units. The units are liters times ATM over moles times K. All right. So this strange unit for the ideal gas law constant tells you what all the other values need to be in, right? The pressure is going to have to be in ATMs, right? The volume is going to have to be in liters. And the number of moles is obviously going to be in moles. And the temperature, of course, has to be in K. Now, we've already stressed that with the combined gas law. We need to use Kelvin for our temperature scale. And so we're just going to keep that in the ideal gas law and make sure we convert to Kelvin if necessary. So let's just use this equation. Let's do a quick example and make sure we can plug in the values correctly. Example 10.3 says a gas occupies 750 milliliters at STP. How many moles are present? All right, so they give us the gas occupies a certain number of milliliters. What is that? That's obviously the volume. Milliliters is a unit that we use for volume. So 750 milliliters. Now, the ideal gas law constant is in liters, so we're going to have to convert that to liters. Super simple. We should be old pros at this now. And so we're going to make it 0.7500 milliliters if we maintain the number of significant figures there. So that's our volume. It's at standard temperature and pressure, so that means our temperature is 0 degrees Celsius. Now, we can't use Celsius, right? We've got to use Kelvin because that's what the ideal gas law constant uses. And so 0 degrees Celsius plus 273.15 is going to equal 273.15 Kelvin. And then finally, our pressure is 1 atm, and that one's fine, right? Because we're at standard temperature and pressure, it's going to be 1 atm, and atm is the unit that we need for pressure. So we've got all of our values, right? We're just going to plug it in this equation here. Again, the equation is P times V equals nRT. And I'm going to go ahead and solve this for moles, all right? If I solve it for moles, I'm going to have to divide both sides by RT, and I'm going to get N equals PV over RT. So let's just plug in those values there. P is 1 atm. V is 0.7500. Look at there. I put milliliters in there. That's not supposed to be milliliters. Let's just scratch that out. That's supposed to be liters. Sorry about that. And then the R is 0.0821. I'm not going to write all those crazy units in there because it would take up too much room. And then finally, our temperature is in Kelvin, 273.15 K, right? And so we plug all of that in our calculator and we end up getting a value of 0.0334 moles. All right, not hard at all. Pretty straightforward, pretty simple. Now, do you remember what happened in the last chapter? You remember whenever we were looking at concentration and we started using equations like molarity and molality. Both of those equations contained moles, right? One of our variables in the equation was the number of moles. And so what I said in the last chapter is it's really common throughout this course whenever you encounter an equation that's got moles in it, to take this equation and then start using it with stoichiometry. So the ideal gas law has number of moles as one of the variables in it. So it should be no surprise that we're going to now use stoichiometry along with the ideal gas law equation. So let's do that example. That's example 10.4. Let me clear that off there. And example 10.4 says a chemist is decomposing KCl into solid potassium and chlorine gas. Now, we got to remember what decomposition is. When we decompose, we take the initial substance and we break it down into its individual components. And so the initial substance is the only reactant, and then the product will be the individual parts of whatever that substance is. So we're going to take this KCl and we're going to break it down into potassium and chlorine. Now, whenever we do that, we've got to make sure that we identify any homonuclear diatomics, and we have one in this equation. Chlorine is a homonuclear diatomic, so we've got to put a little 2 next to that there. And so then to balance this equation, we're going to have to put a 2 in front of this so that we'll have the same number of Cl's, and then we're also going to have to put a 2 now in front of the K so that the K's are balanced as well. So we're good. The chemist decomposed this solid KCl, it says, into solid potassium. All right, let me make a little bit more room here. All right, let's see. So this was solid potassium plus chlorine gas, and this was solid KCl. There we go. And that's important because we're working with gases, and so we're going to focus on the gas in this problem. That's what we're kind of expecting to happen. So anyway, KCl is broken down into solid potassium and chlorine gas. If he does the reaction at a pressure of 1.02 atm, so they give us the pressure in atms, and a temperature of 24.3 degrees Celsius, T equals 24.3 degrees Celsius, what volume of chlorine gas will he make with 50 grams of solid KCl? So we've got 50 grams of this stuff is what we're starting with. All right. And they want to know what volume of chlorine gas is going to be made. All right. So here's what we have to understand. We're using the ideal gas law equation. My hint for that is that it's got P, V, and T in it. Remember what I said before, when you see two different conditions, so like 2 P's and 2 V's and 2 T's, or, you know, you've got multiple of some of those values, then that's a clue to us that we're going to use the combined gas law equation. Here, we're just given the P, the V, and the T for a single gas, and so that's kind of our hint that we're going to use the ideal gas law equation, assuming that this this particular gas could be considered an ideal gas. Now, what's our rule for that? An ideal gas is a gas in which the pressure, we said, has to have a high T, which means the temperature has to be greater than 0 degrees Celsius, and the pressure, we said, has to be equal to or less than, it has a low pressure, so equal to or less than 1 atm. That equal to or less than is a little bit fuzzy. This is really close to 1 atm, so we can consider this one to be ideal. All right. So since we're using the ideal gas law, I am going to go ahead and convert this temperature here to Kelvin. So that means I'm going to have to add 273.15 to that, and that's going to give us a final temperature of 297.5. Sorry, yeah, they run it at 297.5. Yeah, because of the precision there. So 297.5 Kelvin. All right, I think I said significant figures before when we did the temperature conversion, but since we're adding, we got to worry about precision. So this 1 decimal place here, we have to use 1 decimal place here. All right, so we're trying to figure out the volume. Now remember, the ideal gas law is PV equals nRT, right? R is a constant, so we know that value. We're given T, and we also have V. They want us to figure out what the volume is. We're trying to find V. That means we need to first figure out what N is. Well, how do we do that? That's where stoichiometry comes into play. Long before this chapter here, we were already doing problems where they would give us the amount of one substance in grams, and we could figure out the amount of another substance in moles or grams, right? And we followed that path where we would say grams of substance A, we convert that to moles of substance A, then we would convert that to moles of substance B, and we could go further if necessary and convert it to grams of substance B. But we don't need that. For this particular problem, N is number of moles, so we need to figure out the number of moles of Cl2. So that's what we're going to do. We're going to use this path here, and so we're going to go from grams of KCl, that's our substance A, convert that to moles of KCl, right? And then once we find that out, we can figure out the moles of Cl2. That's our substance B. That's the gas that we're trying to figure out. the volume of. All right, so what's our grams of KCl? It's 50 grams. In order to go from grams of a substance to moles of that substance, we go to the periodic table, we figure out the molar mass, and if we look all of that up on the periodic table, we see that the molar mass of KCl is going to be 74.55 grams per mole, right? And so that means in order to convert from 50 grams to number of moles, we do 50 grams of KCl times 1 mole of KCl is equal to 74.55 grams of KCl. Our grams of KCl unit cancels out, and we do the math with that, and we get 0.671 moles of KCl. Now, that's not what we need, though. We need the moles of Cl2 because all of these values here have to do with Cl2. That's what we're trying to figure out is the volume of the chlorine gas, right? So from this, we need to calculate the number of moles of Cl2. And what our balanced chemical equation right here tells us is that 2 moles of KCl equals 1 mole of Cl2, right? Just based on those stoichiometric coefficients in front there. So to go from moles of 671 moles of KCl to moles of Cl2, we're going to take that and we're going to multiply it by 1 mole of Cl2 over 2 moles of KCl. So basically we're going to have half as much Cl2, and we're going to get a value of 0.336 moles of Cl2. All right, now we've got everything we need, right? We're going to use this equation here. We're trying to figure out volume, so I'm going to go ahead and solve for volume. And when I solve this equation for volume, I get volume equals nRT over P. And so just plugging in all the values that I have now for the chlorine gas in this equation, it's 0.336 moles. R is 0.0821. The temperature is 297.5 K. And then we're going to divide that whole thing by our pressure of 1.02 atm. And that's going to give us a final volume of, looks like it's 8.05 liters. All right, so not particularly hard. It's just using the ideal gas law equation and plugging in, using stoichiometry to plug in the number of moles. Now, Avogadro's law is the next topic, and I just want to briefly go over that as we're talking about ideal gases. If I solve for N in the ideal gas law equation, we can see Avogadro's law, right? Ideal gas law equation looks like this. When I solve for N, I get N equals PV over RT, right? We did that previously in one of our examples. And this is Avogadro's law. Equal volumes of all gases at the same temperature and pressure have the same number of molecules or atoms if there's no molecules in the gas. So what does that mean? It means if we're dealing with a gas, it doesn't matter what the gas is, right? If the pressure and the volume and the temperature are all the same, and it's several gases in this system, they all have the same pressure, the same volume, and the same temperature, there's going to be the same number of moles, right? Because R is a constant. And so if P, V, and T are the same, it doesn't matter what the gas is. When we calculate N, we're going to get the same the same number of moles, right? So let me state that again. Avogadro's law. And if you remember, Avogadro's number is that is what the number of moles are, right? That number 6.02 times 10 to the 23. That's what a mole is. We called that Avogadro's number. This is Avogadro's law right here. And again, it says equal volumes of all gases at the same temperature and pressure have the same number of molecules or atoms. In other words, the same number of moles. And so it says this law brings us to an important conclusion. When all substances of interest in a chemical equation are gases, if P and T are constant, the equation gives you the volume of these gases. All right, so the cool thing that this law here tells us is that if we have an equation like this, all right, so let's say we're forming water with this equation right here, right? Notice every single substance in here is a gas, right? And so the way that we've learned to read this is we would say 2 moles of H2 plus, got an understood 1 here, 1 mole of O2, should have just underlined the 1 mole of O2 will yield 2 moles of H2O, right? But what Avogadro's law tells us is that we could also read this as we could use volume values for each of these stoichiometric coefficients. We could say that 2 milliliters of H2 plus 1 milliliter of O2 will yield 2 milliliters of H2O. Again, just looking at the big numbers in the front here, right? Or we could say, we could use another volume unit. We could say 2 liters and 1 liter and 2 liters is what would be produced here, right? So we can read those numbers in the front as volume measurements instead of mole measurements. All right, so that allows us to do something really cool where we can basically do like this stoichiometry type stuff, but do it with volumes when we're dealing with gases. All right, so a quick example of that is example 10.5, which says that we have this equation here, Fe2O3 solid plus 3CO as a gas, carbon monoxide as a gas, is going to yield 2Fe as a solid plus 3CO2 as a gas. All right, and if the reaction consumes 8,615 milliliters of carbon monoxide, so we have 8,615 milliliters of carbon monoxide, then what volume of carbon dioxide is produced at the same temperature and pressure? So how many milliliters, what volume of this, how many milliliters of CO2 are going to be produced? And this is a super simple problem because both of these are gases. Now, it doesn't matter that the other substances in here are solid. The whole equation doesn't have to be gases, but it's just what Avogadro's law tells us is that for the gases, we can say this equation here, if we had 3 milliliters of carbon monoxide, because of this 3 in front, it's going to also produce 3 milliliters of carbon dioxide. And so because that's true, we can say 3 milliliters of CO, carbon monoxide, for this equation equals 3 milliliters of CO2. And so if we have this many milliliters, not 3, but 8,615, how many milliliters of this will it produce? Well, we just use this conversion relationship right here, and we say we have 8,615. You should already see the answer to this one. Should be pretty obvious, but we'll write down the conversion. 8,615 milliliters of carbon monoxide, and this conversion relationship here tells me that 3 milliliters of CO2 equals 3 milliliters of CO, right? Milliliters of CO cancel out. We do the math and we get 8,615 milliliters of CO2. So same number, right? Same number of milliliters of CO2 will be produced as the amount of carbon monoxide that you started with. So that's pretty cool that we can, when we're dealing with gases, we can treat those stoichiometric coefficients in the front of the substances, treat those as volume measurements and use those same stoichiometry relationships like we used before when we were dealing with moles. All right. Okay. I think we're going to end up having one more video and then we'll be done with this chapter. All right. So see you on the next one.